Most people would agree that antibiotic resistance is a burgeoning global problem that could reduce our ability to treat diseases in the future. Although resistance to antibiotics in bacteria can arise as part of a natural phenomenon in the environment, exposure to man-made antibiotics can accelerate this process. When you think of antibiotic resistance though, you probably consider the hospital and the clinical environment, but the truth is, in the agricultural sector, antibiotics are also used. I'm going to try and give you a brief insight into my research on antibiotic resistance on a conventional UK dairy farm. Dairy cattle receive antibiotic treatment when they are sick and during periods when there are increased risk of disease. It is possible for bacteria to develop resistance to the antibiotics they are treated with. Studies have shown that antibiotics are often excreted in animal waste, as much as 70% in some cases. As a result, animal waste can contain resistant bacteria and sublethal concentrations of antibiotics, which are still able to select for resistance. So this is what we're talking about. A single dairy cow can produce as much as 70 kilograms of waste per day. And the average dairy farm in the UK houses between 200 and 300 cattle. That's a lot of waste that has to go somewhere. In typical dairy farming operations, this waste is scraped from the stalls into a pit, and from there it is pumped to the slurry tanks. So the slurry is carried through this pipe to the storage unit. In effect, the slurry tank therefore acts as an enormous mixing pot for the different factors which can contribute to the emergence of antibiotic resistance. However, to farmers, slurry is a fantastic organic fertiliser, and in the UK, around half of all dairy waste is applied to fields. So, the important question is, does slurry application increase antibiotic resistance in soil bacteria? And what management and environmental factors control it? How does the situation change over time? Is it a risk to human health? These are some of the questions I aim to help answer during my PhD, and answering them begins with taking some soil samples. Now we have our samples, let's see whether they contain resistant bacteria. Using selective media, we can isolate bacteria from the soil and purify them. Once we've done that, we can then proceed with disc diffusion testing. All this really involves is applying a disc containing a known concentration of antibiotic onto a microbial lawn of purified culture. Essentially, the larger the zone of clearing, the more susceptible a bacteria is to a particular antibiotic. So, in the case of ciprofloxacin, kanamycin, and nitrofurantoin, we have susceptibility. However, where the microbial growth goes right to the edge of the disc, this indicates resistance to a particular antibiotic. Therefore, in the case of penicillin, ampicillin, and streptomycin, this isolate is resistant. However, most bacteria cannot be cultured in the lab. To examine their resistance, we can extract DNA from the soil. This will allow us to identify most of the resistance genes in the soil. Together, these techniques will allow us to track antibiotic resistance in the soil over time and help establish the relative risk to human health based on data from a conventional UK dairy farm.